In this lecture, we're going to talk about solving the flagpole problem, or another way to say that is we're going to count ordered distributions. We'll show one approach to counting the number of distributions of m distinct flags onto n poles. And let me show what I mean. Here we have a flagpole, and we want to put on some, or here we have several flagpoles actually, and we want to put on some flags. Let's say I have 3 poles, and I want to put on some flags that might look like this. Here you have some flags. Maybe this is flag number 1, this is flag number 2, maybe flag number 3 goes here. Flag number 4 might be here. Maybe we put flag number 5 here and flag number 6 here. We're talking about distinct flags, so each flag is numbered to make it different from all the others. And it makes a difference how we put them on the pole. This is what we mean by ordered distributions. Here 1 is on top of 2. That is different from a distribution in which 2 is on top of 1. Here we have 5 on top, then 3, then 6. If you rearrange these, that would count as a different ordered distribution. So the question is, how many ways can we do this? Well, there are several approaches that are described in the book. I'm going to be talking about the approach that's described in problems 38 and 39, and then later followed up in problem 64. There's a different approach in the text of the book, and in some of the problems, I'll ask you to look at some of those problems on your homework. But here in this lecture, we'll talk about one complete approach. And our approach will start with asking a slightly different question. We'll ask, how many ways can we place m identical flags onto n poles? So we don't care that we won't assume that they're numbered. We don't care about any differences between the flags. All that matters really is how many flags go on each pole. If we have 6 flags, this would be one possible distribution of 6 identical flags onto the 3 poles. The only thing that matters is this pole has 2 flags, this pole has 1 flag, and this pole has 3 flags. Since they're identical, it certainly makes no difference which one's on top and which one's below. There's no sense of order in each pole, because when you have identical objects, it doesn't matter how you order them. Now, this question should look familiar. In fact, we've already answered it, because this is exactly the same question as taking 6 identical balls, since we had 6 flags, and put them into 3 boxes. Say this is flagpole A, flagpole B, and flagpole C. Just imagine boxes instead of flagpoles. Here's A, here's B, and here's C. And we ask, how many ways can I put the balls, 6 balls, into the 3 boxes? Well, this flagpole distribution would just correspond to having 2 balls in A, 1 ball in B, and 3 in C. Counting the number of distributions of identical balls into boxes is the same problem as counting the distribution of identical flags onto flagpoles. And we can answer that. In fact, we have answered that already in the past. The number of ways to do this is the same as the number of combinations of length m from an n-letter alphabet. Sorry, I wrote that badly. N-letter alphabet. In particular, the number of ways to put 6 identical flags on 3 poles is just the number of combinations of length 6 from a 3-letter alphabet. That's just 3 choose 6 with repetitions allowed. And that's just 3 plus 6 minus 1, which is 8, choose 6, which here is the same as 8 choose 2, or 8 times 7 over 2, which is just 28. In general, the number of combinations of length m from an n-letter alphabet, repetitions are allowed because we can have more than one of each letter. This will just be n choose m with repetitions, and the formula for that is just n plus m minus 1 choose m. Once we've chosen how to place those m identical flags onto the n poles, we can now ask how many ways we can distinctify them. That is, place labels to make them distinct flags. I fixed most of those. Let me show you a picture here. Here we have the 3 flagpoles, flagpole A, flagpole B, and flagpole C. How am I going to count the number of ways to place 6 distinct flags now onto the 3 flagpoles? Well, first I'll choose how to pick positions for the flags. That's like counting the number of ways to place 6 identical flags onto the 3 poles. I'm really just picking positions here. That's like putting identical flags here. And then I choose how many ways can I pick which of my 6 distinct flags goes in which of these 6 places. Well, I have the numbers 1, 2, 3, 4, 5, 6, and I want to put these on the flags. And how many ways can I do that? The answer will just be 6 factorial ways to do that. So remember here, I had 3 choose 6 with repetitions, ways to pick the positions for the flags. And then I have to multiply that by 6 factorial. Ways to assign the numbers to the flags. Well, what is that? Remember, that's 8 choose 6 times 6 factorial. 8 choose 6 is 8 factorial over 2 factorial, 6 factorial, and we're going to be multiplying that by 6 factorial. So we end up with 8 factorial over 2 factorial. And we can write that as 8 times 7 times 6 times 5 times 4 times 3. You might wonder why I'm writing it like that. That's just one way we can write the answer to this question. There are this many ways to put 6 flags, 6 distinct flags now, onto 3 poles. Now, here I wrote the answer, but let me say, we now can show, in general, if we have m distinct balls going into n boxes and we're counting ordered distributions so that the orders of the balls in the boxes matters, that's the same as putting m distinct flags onto n poles. So again, order matters, which flags go on top, middle, bottom, or however many there are, in what order they're placed on the flagpole. That number will be, first we'll have n plus m minus 1 choose m. That's just that's just n choose m with repetitions. That's the number of ways to pick the spaces for the m flags on the poles, and we're going to multiply that in this case by m factorial. That's because now if we want to put numbers for the flags 1 through m, there are m factorial ways we can do that, and that product is just n plus m minus 1 factorial over m factorial times n minus 1 factorial times m factorial, so the m factorials cancel, and we get m plus m minus 1 factorial divided by n minus 1 factorial. And we can write that as the product. Think of this as n plus m minus 1, and we're going to multiply that by n plus m minus 2, and we're going to keep going down all the way to 1, but when we divide by n minus 1 factorial, we'll cancel everything beyond n, so we keep going down all the way to n plus 1 and down to n. And here, just written in the opposite order, is the exact same formula. This is the number of ways to put m distinct flags onto n poles. And that's the same as counting what we call an ordered distribution, where we distribute m balls into n boxes, but we care about the order of the balls within each box. Can we modify what we just produced to answer the question, how many ways are there to place m identical flags on n flagpoles, if now we require that no pole is empty? Well, the answer is yes. If we want to put m flags on n poles, but no pole can be empty, the number of ways of doing that, here's an example, no pole is empty. The example I had before had no pole empty, so it would count as well. With that condition that no pole is empty, that's like counting combinations of length m. Remember here the flagpoles A, B, and C. We want combinations of length m from an alphabet of size n with all letters used at least once. So here's in that same example we looked at before, or a similar example to what we looked at before, we have 6 flags onto 3 poles. If we demand that no pole is empty, the number of ways to do that is by standard problem 5, or by, I forget which number it is, that comes from the similar thing for distributing identical balls onto into distinct boxes. We'll just have, what is it, 6 minus 1 choose 3 minus 1, which is 5 choose 2, or 10 ways to do it. That's with no pole being empty. How can we do this in general? To answer this question on the left, it's like counting these combinations. The answer is just m minus 1 choose n minus 1. Again, just by standard problem 5 or the other standard problem, which gives the same result. Now, what if we ask the same question, how many ways can we place m distinct flagpoles instead of distinct flags instead of identical flags on the same n flagpoles, again with no pole empty? Well, again, the answer starts with m minus 1 choose n minus 1. This is the number of ways to place the identical flags, which we can think of as the number of ways to pick positions for the flags. And then we still have to multiply by m factorial, because once we have those positions, we still have to pick which is flag number 1. That might be here, flag number 2, 3, 4, 5, and 6, or there are 6 factorial ways to do that. And I'll just leave that as the answer. You can simplify that in a variety of ways, but that will tell us the number of ways to have ordered distributions of m flags onto n poles, as long as no pole is left empty.